inviting me to speak. Lovely location. Okay, and so I'm going to talk about a joint project with Roman Veshkavnikov, Ben Chang, and Eric Vassereau. This is some description of the center of a small quantum group in terms of some constructible cohomology. So there were previous descriptions in terms of coherent cohomology that motivated conjectures by Lachovskaya and Chi, and this goes part to proving those conjectures. So let me start first with some notation that, even though has been already introduced several times, I want to specify some things. So G is going to be for me semi-simple, and for convenience of combinatorics, it's going to be simply connected. And then again, I'm going to fix a Borel and a maximal torus. And then also the Langlands dual group. I don't know, as it appeared before, though not explicitly mentioned. But it will be the Langlands dual group. And all the algebra, all the small quantum group, will be on the Langlands dual side, and the geometry, the affine Springer fiber, will be on this side of Langlands duality. And then let me introduce a little bit more things of G. This is the Lie algebra of G. Lambda will be the co-weight lattice. Lattice of T, or equivalently, the weight lattice of the Langlands dual torus. And then W tilde is the affine value. Semi-direct product of W with this co-weight lattice group. Okay. And so I'm going to start with the algebra side. So let me introduce a bit about the quantum group. So we've seen already some things about the quantum group. And I want to introduce the small quantum group that has only been mentioned but not appeared before. So as I said, all the algebra, all the quantum groups stuff is going to be on the Langlands dual group. So U nu is going to be the quantum group of the Langlands dual group. And it's some sort of Hopf algebra over Hopf algebra over rational functions in some parameter nu that deforms the enveloping algebra. But I want to consider an integral form that already appeared yesterday. So U nu Lustig is an integral form. It's the Lustig. And it's an integral form over Laurent polynomials. Integral form. Laurent polynomials with divided powers. This is the version that already appeared in Wei Chang's lecture yesterday. This is with divided powers, with quantum divided powers. Okay, but I'm not going to want to look at these algebras over Laurent polynomials, but I want to specialize these algebras at pth roots of unity, or lth roots of unity, going forward. So going forward, we specialize nu to be equal to q some L through of unity. L of 1. And I want L to be odd and large enough. Large enough there just means bigger than the Coxeter number. That should be enough. But I want to consider the quantum group here, because at other generic parameters, the representation theory is semi-simple, the center is easy to understand, and the question is what happens at these special parameters. At these special parameters, the center gets bigger, and we want to understand what the center looks like there. Okay. And so now to define the small quantum group. So the small quantum group is some finite dimensional algebra living in this Lustig quantum group, specialized at Q. So this is generated by non-divided powers, by the regular powers, and just the usual generators, EI, FI, and so on. And this is a finite dimensional algebra. Subalgebra of this Lustig quantum group. And these Lustig quantum group and L through of unity as an interesting map. The Frobenius, the quantum Frobenius, is some algebra. So this UG hat is some sort of version of the enveloping algebra. Such that the representations are the same, the finite dimensional representations of this are the same as the group. So here, it's just the group here is adjoint type. If I'm taking G to be semi-simple, the Langlands rule is going to be adjoint type, so some sort of version where you only get representations with the correct weights. Okay, and so why do I introduce this morphisms? So what you should think of this morphism as is as a quotient by this subalgebra. UQ you can think of as some normal Hopf subalgebra in the Lustig quantum group, and this Frobenius is a quotient map. So in some sense, the Lustig quantum group is some extension of this finite dimensional guy, this small quantum group, and the usual group. And why do we want to consider that? Because it follows from this that on the center, if I take the center of a normal group, the quotient acts on it. And that's what I want to get out of it. The center of the small quantum group is not only an algebra, a commutative algebra, but it comes with an action of the group. Okay, because of this Frobenius morphism being the quotient by the small quantum group. Okay, so what we're going to study is this center with the action of the group. And what we're going to do to study the center is look at it piece by piece. We're going to break the problems into blocks, something that, I guess, not in so many words, but happened in the previous lecture, in Zirkel's lecture. So let's look at some representation theory, of this small quantum group. So here, the Cartan of the small quantum group induces a grading, but only not by weights, but by weights modulo L times weights. So because we're specializing at an L through of unity, this Cartan can't distinguish between some power of q, the trivial power of q and L times the trivial power, an L power of q. L is q is an altitude of unity. And so the Cartan doesn't break the space into all the weight spaces, but sort of can't distinguish by L. But what we can consider is some category where we just add that extra grading. We just incorporate it as extra data. So you want graded. Here's the category of lambda graded UQ modules such that the two lambda not L lambda gradings agree. So we just give it some lambda grading to this vector space, to this UQ module, and we ask that the grading induced, the lambda mod L lambda grading induced by this grading and by the Cartan agree. So we're just adding it as extra data that this category has some weight space decomposition. Okay. And then how does this help us break this problem into blocks, into easier problems? Well, so the linkage principle tells us that this category breaks up into blocks, namely this affine Wall group. Or, well, say, one thing before I say this, let me say what are the irreducible objects in this category. Graded. So the irreducibles are in bijection with now all weights. So there's a highest weight theory for this category, but every weight is allowed. Not just dominant weights, because I have an action by L lambda. I can change the grading by L lambda, shift the grading by L lambda, and that is still going to give us a valid UQ module, a graded UQ module. And so if we have any highest weight, we can always translate it around by L lambda, so we can get all sorts of weights, not just dominant ones. Okay. And then with this, let's look at the linkage principle. So how does this help us break the problem into easier pieces? Okay. So linkage principle. So the linkage principle tells us when two of these irreducible representations could conceivably have non-trivial extensions. So it tells us when they must have trivial extensions. So here there is some action. It's called the dot L action of the affine Wall group on the lattice. Here it's a dot action because it's shifted by rho, by the half sum of positive roots. And the lattice here acts sort of dilated by L. But the case is there's some sort of action. What it is doesn't matter for me. And the theorem says that if I have some non-trivial extension between two irreducibles, then their labels, their highest weights, are related by this action. So it tells us if you have two highest weights that are not related by this W action, there is no non-trivial extension. And so the category breaks up into blocks. So these are the subscript 0 category. This subscript 0 that appeared in the category O in the previous talk. So the category breaks into blocks. And not just the category, similarly the algebra. And UQ also breaks up into blocks. Both the summons of the algebra breaks up as a direct sum of subalgebras, and the category breaks up as a direct sum of subcategories. And these are both called blocks. And we're going to consider one in particular. We're going to consider the regular block. So we consider, I guess, a regular block. We consider the subcategory generated by the irreducibles in the orbit of 0. This is a regular block, and we denote it by UQ0 hat mod grade. And similarly, the algebra, the summoned corresponding to this block in the algebra, we're also going to denote by UQ0 hat. Okay. And so the goal is to understand the center of each of these pieces. And so now,
why is it 0 hat?
So 0 hat is because, in the same way as was explained in Zergel's talk, we can understand this as the center, as some ideal of the center acting nilpotently, and the hat here denotes this nilpotency. It's sort of set theoretically supported at some ideal, as opposed to scheme theoretical, which I would denote by 0. You? But with this, you can then state the conjecture, the original conjecture about the center that motivated this result. So this is N G. So I'm going to state it for type A, where the conjecture was sort of the most ambitious. So in type A n plus 1, I guess. G acts trivially on the center UQ0 hat, and the dimension U0 hat is n plus 1 to the n minus 1. So this number here, n plus 1 to the n minus 1, is also the dimension of the diagonal covariance. I will get to that also towards the end when I talk about the newer results. But this was sort of the original conjecture. So this G action on the center that we had to describe, in fact, turns out should be trivial in AN. It should not be trivial in other types. In fact, it isn't trivial in other types. But the thing we proved, the thing we've proven is not this part. We prove that the G invariant part has this dimension, but we still have to prove this first part. So in some sense, we've proven that this first line implies the second, but still haven't proven the first line. Okay.
For all types or just in type A?
So we've proven something for every type, but the strongest results are in type A. I will get to it, but there's a question of whether the diagonal covariance, the Daha representation of the diagonal covariance is irreducible or not. And this type A is, and so that gives you the strongest result.
And it should be noted that in other types, the first statement fails.
Yes, I think I said that. Yes. Okay, great. So this is the conjecture, and that's what we are going to work towards. But any questions?
So you proved that the G invariant part of the center in type A has the dimension.
Correct. Yes, and in general, we have a bound of the dimension that it's at least whatever this equivalent should be, and at most the diagonal co-invariant, the dimension of diagonal co-invariance in that type.
Is the type of an plus 1 or an minus 1?
Minus 1, sorry. Very difficult. Thank you. Yeah, SLN. Okay. Yeah, any questions about this? This is the algebra part. Otherwise, I'll go into the geometry.
Do you have doubly action on this?
Yes, we have on this Q0 hat, we have an action of, in fact, something like W tilde, semi-direct product C of H. This is the Lie algebra of the torus. But the problem is we can't deform this to a Daha action here, because this small quantum group does not deform. Because when we deform Q away from an L root of unity, this small quantum group stops existing. This small quantum group only exists at this special parameter, and so yeah, it's unclear how to deform this center to some Daha representation, and that's precisely sort of some complication of the proof that, you know, in the deformed version, so the affine Springer fiber does deform, and there we can prove that it's irreducible as a Daha representation, but here we can't because we can't.
But like this particular action, so you can define it just within the quantum group.
Yes, yes, yeah. This is just some, comes from some action, some braid group action on the derived category of UQ0. This part here, some affine braid group action, I guess, due to Simon, right next to you. This part is explicitly identifying some part of the center here. So it's just by multiplication by some particular central elements.
So can you say again how you define the W? So is it geometric definition of the action of W tilde on the center?
So the statement, I guess, maybe a Rieschen Beschwerdhavnikov. Wow. Maybe plus something. Okay, is that on the derived category of UQ0 at mod graded, here there's an affine braid group action. Ver is the affine braid group action. And an action here induces an action on the center of this category, and you can check that the induced action on the center factors through W tilde. This is the construction of this W tilde action, and as I say, this part is used there.
Yeah, and another question. So you can just consider UQ as a true subalgebra in the, so without any grading, right? And this conjecture was actually for the center of that. Yes. And these are the same, right? So basically.
So this is the ungraded version. I have introduced the graded version because in the geometry of the affine Springer fiber, it's more natural, sort of the natural answer consider this the graded category. But I just use the graded category to understand the ungraded category. Yeah. But somehow the affine Springer fiber is naturally graded. Okay, good. So any other questions?
Excuse me.
Yes.
The graded category is just a category of weight modules of unrolled quantum groups. It looks like this.
Of weight modules?
Of unrolled quantum groups. Unrolled quantum groups. It's the extension of small quantum group by Cartan.
Yeah, exactly. Yes.
And then you look at the representations called weight
Yes.
modules, which are where two weights of two Cartans agree. I mean,
Yeah,
K
yeah,
and A.
it's a Harishchanda pair of UQ and the torus. That's what this thing is saying. So yes.
Yeah, you have integral weights.
No, restricted unrolled.
Restricted.
Yeah. With integral weights of unrolled.
Yeah. So you need the torus, the actual torus group, in order to have just integral. Okay, great. Any other questions about the algebra? Okay. then I want to introduce these affine Schwinger fibers that are going to help understand this center.
While you're raising, do you get any information about double coinvariance in all types? As far as I know, there is no formal what you mentioned.
Do we get any information? Not anything that we can't get some other easier way.
Isn't it h plus 1 to the
No, this is the Chernik thing, double coinvariance.
Oh, yeah, but the answer probably will be Cherednik thing. I'm not sure, but
Yeah.
it's probably more likely.
Yeah. It's more, we use information of diagonal coinvariance to prove this. It's more in that direction. Okay, great. So then let me introduce the geometry. So affine flag varieties. And Schwinger fibers. What are the geometric objects that we're going to use to try to describe center? So K is going to be Laurent power series, and O just regular power series. And then we're going to introduce, now again on the side of G, so now we're on the other side of Langland's duality. So we consider the affine Grassmannian as the quotient of G of K, G with values in Laurent power series by G with values in regular power series. So this is the affine Grassmannian. And the flag variety is some G mod B bundle. So some finite flag variety bundle over this infinite dimensional affine Grassmannian. The affine flag variety. And it classifies some subgroups of G of K known as Iwahori subgroups. In the same way, it classifies Iwahori subgroups some subgroups here in the same way as the finite flag variety classifies groups conjugate to the Borel, classifies Borel subgroups. Okay, and so this is the affine flag variety and the affine Grassmannian, and we're going to consider inside these very infinite dimensional objects some finite dimensional things, some finite dimensional varieties. In scheme still, but and consider the cohomology, the sort of Borel-Moore homology, I guess, and this constructible sheaf cohomology of these spring fibers. Let me define what they are. I guess this definition is due to Kaczna and Lustig. So for some element in the loop Lie algebra, so in the Lie algebra with values K in the Laurent power series, we can define FL sub gamma as those Iwahori subgroups in FL that contain in its Lie algebra this particular element. Okay. So this thing here is particularly interesting when gamma is semi-simple. when gamma is semi-simple, this is going to be some finite dimensional, or rather regular semi-simple. This guy is going to be some finite dimensional guy, and we're going to study this. So we focus, we consider the case when gamma is equal to Ts. And so what's Ts? So T is the parameter, this variable in the power series, and S, where S is in the Lie algebra of the torus, is regular semi-simple. Okay, so we're going to consider that element, and that's the element Ts that is going to be related to this small quantum group. Okay, and maybe let me just say, if we consider something similar like this, but on the Grassmannian, this is sort of related to Jacobians of some curves with singularities. And I don't know if somebody else will talk about it in the future talks, but. Here. Okay. So let me say a few things about this particular variety. What does this variety look like? So, first thing is, as I said, it's some finite dimensional guy, and in fact is the same dimension as the finite flag variety. Just say geometry of FLTS. So the first point is it's equidimensional. So what does that mean? This means that every irreducible component has the same dimension, and each of them has dimension, the dimension of the finite flag variety. And as I say, this finite flag variety is one of the components, one of the irreducible components in this affine Springer fiber. And this affine Springer fiber has some actions. So the loop torus, the torus with values in Laurent power series, centralizes Ts because it's an element in its Lie algebra and it's a commutative group. So it centralizes Ts, and so it acts on FLTS just by left multiplication. It acts on FL by left multiplication, and because it centralizes Ts, it fixes this FLTS. And out of this, we get two actions. So we get first a T action. If we just consider the constant part of this group, the part where the coefficients are all constant. And then we also get a lattice action. So how do we get this lattice action? So there's in fact a group homomorphism, maybe by choosing some uniformizer, say T, some group homomorphism from lambda, from this co-weight lattice of T to this loop torus. And so through that homomorphism, we get an action of the lattice on FLTS. So this is a space together with some lattice translating it around. And in fact, this lattice, so lambda, acts freely on the set of components. With the size of the Wall group, many orbits. Okay, so this space has infinitely many components, that are all translated, or such that W, they form W different orbits under this translation by the lattice. So in some sense, there is a bijection between irreducible components and the affine Wald group, W times this lambda. So just to see what it looks like in some concrete case, let's look at it for SL2. So for SL2, it's really easy. So it's of dimension 1 because of the first line over there. And what does it look like? So for SL2, it's just an infinite chain of P1s. So these are all P1s. Infinite chain of P1s. And what does the lattice do? The lattice translates by 2. Translate by 2. It translates one of these components by 2. So that there's 2 different P1s up to the action of this lattice. Let me just say, so the components are smooth for SL3, but already some singular components in SL4 and higher type A cases and in B2 and any type B case. So there's a lot of very complicated singularities in these components, and these spaces get very complicated as the rank increases. Okay. So what the result will be is some comparison between the cohomology of these spaces and the center of the small quantum group. So let me try to introduce the cohomology of this space, where we will see all these actions that we talked about before. Okay, so I guess the theorem, which I don't know. There's some part that's, I guess, Sage and Baragnola-Vassero and Ewan, Ewan. Many people, and the other part. Joint work with Ivan Lossev, okay, which tells us that on the Borel-Moore homology, on the T-equivariant Borel-Moore homology of this FLTS, there's a bimodule. There's a bimodule action of this W tilde semi-direct product, C of H. So this gadget we saw before acted on the center here on the Borel-Moore equivariant, on the equivariant Borel-Moore homology would have a bimodule, bimodule structure. So we have in fact 2 actions. And what are these actions? So the first one, the one that's due to all the previous people, is the Springer action. Introduce this, but on these affine Springer fibers, there is some Springer action of W tilde. And then this Lie algebra of the torus acts by Chern classes. So this is some action that had been studied before. And then the other one is extending this lattice action. So there's this geometric lattice action, and in fact, it extends to a W tilde action. So translation action extends to a W tilde action, and then C of H acts via equivariant parameters. But so this here we are looking at equivariant Borel-Moore homology, and so the T equivariant cohomology of a point acts on it, and the T equivariant cohomology of a point is exactly that. So that's what I mean by this. Okay, and then maybe here. What else follows from this? So we not only construct this bimodule action, but in fact understand this bimodule action in terms of some geometry of Hilbert scheme of points on C2 or analogous geometries for other types. But what I want to record here is the dimension. So the dimension, if we consider the Borel-Moore now no longer equivariant, FLTS, and we consider the W tilde coinvariance. So this is this action, the action extending the translation. Action extending the translation. This, in general, is the Coxeter number plus 1 to the rank, or in the case of type A, n plus 1 to the n minus 1. Here we see again this number, and this, or really the dual of this, is what we're going to want to relate to the center of the small quantum. Okay, so any questions about the geometry of this affine Springer fibers? Go into results.
So the whole homology of this affine Springer fiber, do you have interpretation in terms of?
Yeah. So for okay, I'm going to write something that I would need to be careful, but so this homology, T equivariant homology of Borel-Moore homology of FLTS, modulo some being careful, is Homs of the Purchesi bundle to the Purchesi bundle twisted by 1. This is the Purchesi bundle, where we're considering here Homs in over the Hilbert scheme of points of C2 or some sort of analog of this for other types. But this gives some description of this Borel-Moore homology in terms of that Hilbert scheme of points geometry, and that's sort of how you can get to this picture. In fact, to get to this result here of dimension, you get one bound here and the other bound here. So you sort of need these two geometries, this constructible and this coherent geometry, to prove this dimension.
Right, but like this thing in terms of quantum group as well.
So yes, so the in terms of the quantum group, yeah, maybe I'll. Okay, I was going to state it right now, but yeah, so the quantum group is not going to be related to Borel-Moore homology, but to its dual, to the cohomology. And we have some category whose center is exactly this guy, this T equivariant cohomology. So that one can just be proven, and then from that it follows all the results that I'll state there, because we're quotienting, and then the center could a priori grow. So that's the issue. Yeah, but I'll state it right now.
Well, the equality in the bottom line is only true after some completions.
Yeah, that's why I kept insisting. This is a lie, but I don't want to describe the conclusions. Okay, thank you. Any other questions about this geometry of LTS? So then let me take the first connection to the center, and there I will be able to explain a bit better this connection discussed with Eugene. Okay, so what's the results of the center? Hat. So theorem joined with Beshukavnikov, Shan-Vasaro, is that there exists a commutative diagram where here we're looking at the dual of the Borel morphomology to cohomology, and now instead of looking at co-invariance, we're looking at invariance, but still this is the same action. This is the action extending the translation action. This W invariance, W tilde invariance, map to the G invariance under this group action. If we just take lattice invariance, so don't take invariance of the whole thing, but just lattice invariance, then this lands in T invariance. And then how do we get these two results? So these two results come from a bigger map, which is this motivation of considering the graded category. There is some map from the full cohomology into the center of this graded category. And so what do we need here by the center of a category? So the center, next slide. So here by the center of a category, we just mean the endomorphisms of the identity functor, which if we're considering A mod, so if we consider the center of A mod, this is just equal to the center of A. So it is some way of writing the center in a different way. But right, so here, in order to get this homomorphism, we have some deformation of this category where we identify this T equivariant cohomology as the center, and then we get an induced map. Because we have taken a quotient, the center could a priori increase, and so we only get a priori these inclusions. But the conjecture is that all these maps, all these maps going across are isomorphisms. Okay, so these were the previous results, and now I want to talk a bit about progress in proving that this is an isomorphism. We can prove that that is an isomorphism in type A, and always bound sort of how bad it can be away from being an isomorphism. Okay, so any questions about this statement? One? And maybe let me say, since we brought up all these actions, all this is still compatible with the actions that we described. So here we've just killed one of the two actions. We've killed this second action on the left-hand side. But there still remains the Springer action. And the Springer action here is going to correspond here to this action by W tilde semi-direct C of H that I described before. So this is some map of modules like this. So this again, why I was talking about deformations. If we had some valid deformations, we know this is irreducible. So if we prove this is irreducible, we would be done, but we don't have a deformation of the right-hand side. Okay, so any questions? Yes? Now let me talk a little bit about the questions of surjectivity of the first map, the G invariant. And so this, again, comes motivated by some geometry, which sort of motivates ongoing ideas about other surjectivity. But let me just say, as I mentioned, G mod B is some component of FLTS. And so from this, we get some map on cohomology. And the good thing that we can see this sort of map on the algebraic side. Namely, there exists some object, in fact a projective object, on UQ0 at mod graded, such that the endomorphism of P0 is the cohomology of G mod B, and the action of the center factors through that map. And, well, the action sort of the center through this map factors like this. And the action yes factors through restriction, through this restriction map. And so what we can try to look at is not just this P0, but somehow P0 together with all the possible actions by this Springer action. So what we're going to do is act on the category by this braid group action to create some elements P lambda. We can create some elements. These are all derived, well, except P0. These are all complexes for lambda and lambda. And what's the upshot of this is that we get some object where the action of the center can be proven to be faithful. So, the result, position, the action, the only action that we can prove is faithful is of this G invariant part. Faithful on this object. If we could prove that this action was faithful on some slightly bigger center, let's say on this would be the most ambitious thing, but even on something slightly smaller like this, we could get a stronger result about surjectivity on these other pieces. But okay, we have that it's faithful on this part of the center, and from this, again, working a little bit more, we know that the center injects into the endomorphism of this object, but working a little bit more, we can construct some injective map from this G invariance to the dual of diagonal covariance. H times H modulo H times H plus W dual. Basically, we can see that this guy, this dual of the diagonal coinvariance, lives as some part of the endomorphism algebra of this big object, and we can prove that the center lands there. And so what we have is a commutative diagram injecting here like this. And now in type A, by Hyman, this thing here, or these two ends here, have the same dimension, so this is an isomorphism. In other words, it's telling me that this center is between something of dimension n plus 1 to the n minus 1. So an isomorphism. So let me just state and then final result. So corollary. Type A. The dimension of this UQ0 hat G invariance is n plus 1 to the n minus 1. And so we get from this that if the action is in fact trivial, we would prove the conjecture as required. And one way to prove this is proving this surjectivity here. If we prove this surjectivity here in type A, the conjecture of Lachowska and G would follow. This G invariant would follow. So maybe let me finish there and wait for questions.
Questions?
So before the center statement, there should be a categorical statement of modules over small quantum groups should be corresponding microlocal sheaves.
Yeah, I can.
If you have,
I can state that. Also, I ran out of time. Okay. So yeah, so there's a categorification of this result, which doesn't only relate the center, but relates the full category of the small quantum group representation, or these graded small quantum group representations, to the Springer fiber. Namely, this is ongoing work with Bekhokovnikov, McBreen and Yoon. And okay, so it states that some sort of category FLTS, microlocal sheaves on FLTS, whatever that is, some sort of category that sort of lives on this Springer fiber is, let me say, causal dual. Again, this causal duality is something that we also saw in Sorgel's talk, and we're going to see more in future talks. But it's causal dual to this graded quantum, small quantum group representation. And from here, for example, if we have some smooth component here, X is smooth, then there is some sort of constant sheaf on X, some object that looks like a constant sheaf on X, whose endomorphisms, or whose X algebra, it's just the cohomology of X. And this thing is going to correspond to some sort of projective object here. Again, this correspondence in causal duality between irreducibles and projectives. So from this picture here, we get some projectives whose endomorphisms are the cohomology of some smooth components here. And many more results in this direction. In particular, other approaches here, where we can sort of consider some nice filtrations on this FLTS that will give us some nice filtrations on the category that might be used to prove this, but given that I don't have much time, let me, if somebody's interested, they can ask more questions. But yes, bottom line, there is some categorification of this result, and from this result here, we can recover, again, this map here. So there is some categorification from which this follows.
All right. Other questions?
Yeah, I sort of have a question. So maybe first question is, do you have an idea about extension of the duality on level of monoidal categories? When you have to take all blocks.
Okay.
I know it's not monoidal, but you have to take all blocks. Right?
Yes. So if you take all the blocks, yeah. I mean, here just you can, I guess, take it as a direct sum of these microlocal sheaves category, but it's unclear how to construct some monoidal structure on this union. I mean, yes, that would be very interesting, and
not even an idea.
It's unclear. Yes, it sort of mixes it in some weird way. So yeah, we don't have a good figure for it. Because the way it plays with blocks is sort of complicated.
In the center is a zero Hochschild cohomology of small.
So here, the center here, because of Koszul duality, corresponds to the pure part of the Hochschild cohomology here, and the pure part of the Hochschild cohomology here, again, conjecturally, is just the pure part of the cohomology of the space, but the space is already pure. The cohomology of the space is already pure, so it's just all the cohomology.
You have a conjecture for higher homologies of the principal block?
No, I mean, we haven't. They've worked about it. I don't know if they have some conjecture, but no. But so because this Koszul duality doesn't send the center to the center. It sends the center to some other part of the Hochschild cohomology. Like the Hochschild cohomology is bigraded, but this map here, like it changes the grading.
I see. My question was about Hochschild cohomology on the right.
Right. So the Hochschild cohomology on the right, I haven't considered, but
There is some other interpretation.
No, I know your work was
So,
yes.
all right, so I wanted to ask a little bit here about the proof, because I think the result by Hyman was known before, right? So this inclusion was. Also, the vertical one, it's your work before, right? So that was also known. So what remains is this, and that's based completely on this result, which is completely representation theoretical, right? It's just basically representation theory.
Correct.
So it's so this thing is just done by considering projective modules and the action of the center.
So it's not projective modules. So these p lambdas are not the projectives. These p lambdas are, you start with this the projective that you get from starting with the most singular block and going to the regular block, and then you act by the braid group. So these
are complex.
These are complexes, yes. So they're complexes. So it's a slightly smaller endomorphisms, which makes life easier. But yes, that's exactly right. You're working with these complexes, and we can prove.
And somehow you relate these complexes to this to the dual of diagonal coinvariance.
There is a map from this dual of diagonal coinvariance to the so here we know it lands on the product of cohomologies of G mod B, because the endomorphisms of each of these, and we construct a map from here to here, and in some sense it's characterized by the action of this W tilde semi-direct product H, and we prove that the center has to satisfy those conditions, and so it lands in that guy.
Yeah, but still the cohomology of G mod B is coinvariant, it's not double coinvariant. So
Right. There is a map from double coinvariance to here. There is no, it's not equal.
I see.
Yes. It's basically by evaluating, here you have a lambda, so you evaluate one of the two parameters with lambda or something.
Thanks. And other questions?
Yes.
So you have a basis in diagonal coinvariance in type A that Eric Carlson and Alexa constructed.
Uh-huh.
Like, basically using this embedding in some sense. But do you know if this basis would correspond to some basis in the center?
So in the center, I don't know. Good question. In the cohomology of the Springer fiber, I guess this should be something like the Schubert basis, if I'm not mistaken, or maybe plus or minus. but no, in the center, I don't know how to describe it. And, you know, in fact, sort of, yeah, I don't know how to describe elements in the center sort of independently from this map here. Only very special, like the top cohomology elements in the center here have a clear description here, and maybe the cohomology of G mod B has a clear description here, but all the other elements, yeah, I don't know exactly how to describe these central elements directly.
You know anything about algebra structure? You know, double covariance has some algebra structure.
Yeah, so I mean, the algebra structure here is the same algebra structure as here. So it's not using this algebra structure of the diagonal covariance.
No, diagonal covariance algebra structure does not appear.
It's known that the multiplication at the center is not the same multiplication as in the diagonal coinvariance, even in the case of SL3. So that means there is another multiplication on the diagonal coinvariance.
As I say, I think the appropriate thing is there is a multiplication on the dual of the diagonal.
Probably it's the better to see.
Look, and what comes from Chernykh algebra also doesn't match with the double covariance.
Maybe. Yeah. Okay, the question.
Yeah, I mean, for me, this small quantum group was always sort of G1T modules. I mean,
yes.
There's this characteristic P analogon.
Yes.
How much of this is same for?
So many things are safe. So okay, so this map here is safe. This is purely purely representation theoretical. This not at all, because the constructible things with modular coefficients are harder. Here, so this bottom part here is fine. The top part here is fine with some caveats. So this part is harder. So in order to, I still think it, in type A it should still be true. Maybe for large P, everything I'm saying for large P. For large P, that we can still prove this result in type A for G1, regular block of G1. Yes, so many things yes, but some things no.
Okay, other questions? All right, so then let's thank the speaker again.